Hello everybody, NVIDIA Jensen Huang is hosting a panel titled The Transforming AI at GTC 2024, featuring 7 key minds in the field. Among them are the authors of Attention is All You Need, the groundbreaking paper that introduced the transformer neural network architecture. Transformers have since revolutionized all areas of AI, dominating the industry. However, the panel agreed that the current transformer model doesn't fully meet their needs. They will elaborate on this during the talk. Enjoy the discussion and don't forget to like, share and subscribe if you like the contents.
Please welcome to the stage NVIDIA founder and CEO Jensen Huang.
Apparently, there's a huge line out there, and they're orderly, in an orderly way, coming into this room. But once they come into this room, it becomes total mayhem. What is it about? Come on, you guys, hurry up, I'm gonna start. So this room is gonna be packed. And there are 2 other breakout rooms. They're going to be packed. And it's just that they're taking too long getting in here because they're just timid. And the part that I just don't understand is once they get in here, once they get within about 10 feet, all of a sudden chaos ensues. It's very, very nice to see all of you. The computer has largely remained unchanged for 60 years. The year after my birth had nothing to do with my birth, but the year after my birth, the modern computer was described by the IBM System 360. The central processing unit, I/O subsystem, multitasking, the separation of hardware from software, software compatibility across a family, backwards compatibility to protect the investment of software engineers. I describe modern computing. Hasn't changed, 1964. In the late 80s and the early 90s, the PC revolution kicked it into turbocharged, democratized computing as we know it, driving the marginal cost of performance down every single year. Every 10 years, we reduce the cost of computing by about 10 times. Every 5 years. Every 10 years by 100 times. 15 years, 1,000 times. 20 years, 10,000 times. In literally the 20-year era of the PC revolution, computing costs reduced by 10,000 times. More so than any other valuable commodity in history. Could you imagine if everything in life reduced, everything that matters, everything that's valuable to you, reduced in cost by 10,000 times? 10,000 times over basically half a lifetime, 20 years. By the time you became an adult, something you used to use, like a car, used to be $20,000, now it costs $1. Well, maybe that's Uber. But computing costs dropped tremendously, and then one day it stopped. Not precisely one day, but it stopped. The rate of change stopped. It still continuously improved a little bit every single year, but the rate of change stopped. Well, we worked on another form of computing called accelerated computing. It is not as easy to use. There's nothing easy about using accelerated computing because you have to formulate the problem from what is originally kind of like a recipe, step by step by step, that you do faster and faster every year. But you have to reformulate a recipe into parallel algorithms. Parallel algorithms is a whole field of science. Insanely hard to do. Well, we believed it anyways. And we believed that if we could accelerate the 1% of code that represents 99% of runtime. There are some applications that we can make a tremendous benefit, a tremendous difference. We can make something impossible possible, or something that costs a lot of money to do cost effective, or something that costs a lot of energy to do energy efficient. And so we called it accelerated computing. We worked on it for the entire duration of our company's history. And one application domain after another application domain, we were able to accelerate. The first one was computer graphics and video games. We accelerated computer graphics and video games so well that people thought we were a computer games company. But nonetheless, we kept pursuing it. We realized the value of computer graphics and games because it was simultaneously a large market and it drove technology innovation. That rarely happens. The confluence of large markets that is never good enough has the ability to drive incredible technology revolutions. We found it initially with computer graphics and games. Well, make a long story short, in 2012, we had a first sighting, and that first sighting was AlexNet, the first contact of artificial intelligence with NVIDIA GPUs. And it started our attention to this field. Several years later, something amazing happened, and it led to today. Today is, I'll tell you about that something in a second. That something led to generative AI. Now, you've heard me say generative AI is, of course, incredible. The fact that software can not only recognize an image of a cat and say cat, it can take the word cat and generate an image of a cat. It can take the word cat with a few more conditional prompts, like on a surfboard, on a sunny day, off the coast of Maui, drinking a Mai Tai, wearing a ski hat, whatever, you just keep on adding your prompts, and somehow the generative AI is able to generate that. We have now taught a software program how to understand the meanings of these pixels, to recognize the pixel, understand the meaning of the pixel, and in fact able to generate from the meaning of something pixels. And so this ability for us to learn data from learn the meaning of just about any data is incredibly transformative and has led to today. You've heard me say that this is the beginning of a new revolution, a new industrial revolution. And there's a reason for that. In this new industrial revolution, we're producing something that never existed before, as in previous industrial revolutions. The last one, water comes into a facility, energy is applied to it, this thing called a dynamo goes off to work, and it creates this invisible thing of incredible value that we depend on today. Water comes into a building, you basically light it on fire, you boil it, and what comes out the other side of it is electricity. Water in, electricity out. Magic. Electricity used everywhere. And created the Industrial Revolution as we know it. A new facility creating a new product of great value. Well, generative AI is a brand new type of software, and the software is produced. It, of course, has to be created. Amazing computer scientists have to go create it, but then after that, it's produced. It's produced in volume. A building with a machinery we call GPUs, essentially a dynamo, a large building with machinery inside. You give it raw material. This raw material is data, numbers. You give it energy, and this amazing thing comes out. Numbers. Numbers go in, numbers come out. And the numbers that come out do amazing things, unbelievable things. And they could be used of course, in all of the applications that you know, but it could be used in healthcare and drug design, and could be used in transportation and cause cars to drive, and manufacturing and industrials, and every single industry that we know will benefit from this new product, that is this new thing that is being produced. So a brand new thing that the industries have never seen is going to get produced, and it's going to be produced in facilities and factories the world's never seen before. AI factories, producing AI, and the AI being used by every industry. So what do you call that? A new industrial revolution. None of this existed. None of this existed before now. And we're seeing it play out right in front of us. This next 10 years, you don't want to miss. You don't want to miss this next 10 years. Unbelievable new capabilities will be invented. And it started at a point in time by some researchers. And so today I thought we would invite the inventors, the creators of a machine language model called Transformer. And the way we thought we set it up is kind of like our living room. And there will be very little moderation. We were in the back, and I wish you were there. There were a lot of deep learning jokes. A lot of deep learning jokes. And we're going to see if any of them land, but a lot of good deep learning jokes and a lot of arguments. And so I thought I would do is we would just tee up the joking and the arguments, and then we can see where it takes us. And so what I would do, let me now welcome the inventors of the Transformer, and they were the authors of the paper that says attention is all you need. Okay, so let's have Ashish Vaswani. Ashish. Ashish is now the CEO of a brand new startup company called Essential AI. Noam Shazir. Welcome, Noam. He's also a CEO of a new startup called charcter.ai. Somehow all of their startups have a name called AI. NVIDIA also has AI, just not in the right order. I knew it all along. That I needed the letter A and the letter I in there. I just didn't know what order it had to be. Jacob Erskorzitz. Jacob, nice to see you.
See you.
Jacob is also CEO of a startup. CEO, this is really, really interesting, inceptive. Okay. Yeon Jones. Founder and CEO of sakana.ai, welcome. Aiden Gomez. Founder and CEO of Cohere. My goodness, Lucas. Come on, Lucas Kaiser. Ladies and gentlemen, the only person who is still an engineer. Lucas, yeah, you're my hero. Ilya, come on the stage. Poloshukin. Near Protocol. He's a co-founder of Near Protocol. Okay. And we have a colleague and friend who couldn't make it because of a family emergency, and so our hearts and thoughts are with Nikki. So let's so first of all, they've actually never been in the same room at the same time.
Mm-hmm. That's true.
This work from home thing is out of control. But apparently it doesn't stop innovation and invention. And so it's great to have you guys here. You know, the transformer was and we're going to talk about the importance and the meaning of the work, the incredible transformative capability of the transformer, and what it has done to industries. And obviously, as I was saying earlier, everything that we're enjoying today can be traced back to that moment. The fact that we can learn from data of gigantic amounts in a sequenced way, sequential data as well as spatial data, but learn from just a tremendous amount of data to find relationships and patterns, and to create these gigantic models was really quite transformative. My first question, and you guys all dive into it, and we agreed that it is not impolite to cut each other off, talk over each other, disagree with each other, even get out of your chair.
You need a whiteboard then for that.
We need a whiteboard, that's right. Nothing is off limits today. But go back to the beginning. What were the problems? You know, engineers, we need problems to inspire us. What were the problems that you were struggling with or challenged with that led to this?
I think everybody had a different problem probably, but for me and the team we were working on question answering. So very simply, you go to Google, you ask a question, it should give you an answer. And Google has very low latency requirements. And so if you want to ship actual models that read, you know, search results, like tons of documents, you need something that can process that really quickly. And models at the time, recurrent neural networks, just cannot do that.
Yeah, because there were recurrent RNNs, yeah. and RNNs had some attention, but you know the difference.
They need to read word at a time.
They need to read one word at a time. That's right.
We were generating training data much faster than we could actually train the most advanced architectures on, and so you actually had simpler architectures, just feed forward nets with n-grams or so as input features, that because they trained so much faster on, you know, at least in some problems at Google scale, massive amounts of training data, they basically always outran the much more advanced, much more powerful RNNs at the time, or LSTMs. And so it seems like a valuable thing to fix.
Yeah, we were already seeing these scaling laws back in like 2015, and like you could see, you make the model bigger and it just gets smarter, and here is like the best problem in the history of the world. It's so simple, you're just predicting the next token and it's going to get like so smart and be able to do a million different things, and you just want to scale that up and make it better. And one just big frustration is like RNNs were just a pain in the you know, to deal with, right? And then, so I overheard these guys talking about, hey, let's replace it with convolution or with attention. I was like, heck yeah, let's do this. And I think it was, I like to compare it to like, you know, RNNs were like the steam engine and transformer is like internal combustion. Like we could have done the Industrial Revolution on the steam engine, but it would just have been a pain in the butt, and like things went like way better, you know, with internal combustion.
So now we're just
electric vehicles.
Yeah. Now we're just waiting for the fusion, right? That's the next wave.
Yeah.
I mean, two lessons that I was reminded of constantly, especially during the time of the transformer, was I started tasting some of the bitter lesson when I was in grad school, when I was working on machine translation, where I felt like, hey, I think that gradient descent, the way we train these models, is a much better teacher than me, so I'm not going to learn these linguistic rules. I'm just going to ask gradient descent to do everything for me. And the second piece was that, you know, I mean, just quoting from the bitter lesson, the general architectures that can be scaled are ultimately going to win in the long run. Today it's tokens, tomorrow it's actually the actions we take on a computer, and they'll sort of start mimicking our activities and be able to automate a lot of the work that we do. So the transformer was self-attention in particular, as we were discussing, it had this quality that was extremely general. And it also made gradient descent happy, and the second thing it made happy was physics, because I guess like something I did learn from Noam over time is matrix multiplications is a good idea. So let's try to make accelerators happy, and both those things together, this motif has been repeating. So every single time we add a bunch of rules, gradient descent will one day learn those rules better than you.
And this was it. Like all of deep learning has been, we're building an AI model that's the shape of a GPU.
Yep, that's
and
right.
now we're building an AI model that's the shape of a supercomputer.
Yeah,
And,
the
you know,
supercomputer is the model now. Yeah, that's true. Yeah, the supercomputer's the, yeah.
Just so you guys know, we're building the supercomputer to be shape of the models.
Yeah.
That's right, yeah. That's right, yeah.
Now, what were the problems you guys were solving?
Oh, machine translation,
Yeah.
definitely. And it seemed so hard 5 years ago. Like, you had to gather data, maybe it would translate, maybe it would be slightly wrong. It was like the very basic level. Now these models, you don't get any data at all. They just learn to translate. You have this language, that language. It just emerges that the model can translate, and it's very
But
good.
what was the intuition that led to attention is all you need?
So I came up with the title, and basically what happened was, at the point where we were looking for a title, we were just doing ablations, and we had very recently started throwing bits of the model away, just to see how much worse it would get, and to our surprise, it started getting better. It's including throwing all the convolutions away. I'm like, this is working much better, and that's what was in my mind at the time, and so that's where the title comes from, basically.
But what's intriguing about that is we actually kind of started with that bare bones thing, right?
Yep.
And then we added stuff, we added convolutions, and I guess later on we kind of knocked them out. And it was, you know, a lot of the other things like multi-head attention that, and it was also really a super important piece. But I was watching this movie, I don't know if you've watched it, Leon, where this guy's in a parallel universe where they don't have Beatles, Beatles didn't exist anymore. And I was wondering what would be the title in that universe. I don't know if you watched it, I forget what it's called, Yesterday or something like that.
Yeah, no idea, sorry.
He's got no time. He's trying to build a company. And so then you guys, well, hey, this is important. How did transformer come up? What were some of the other choices? Who came up with transformer? Why is it called transformer? It's an excellent name, by the way. I think it's
you, the
fantastic.
transformer, right?
No. I liked the name that Jakob had for it. I was like, that's a
Jakob.
cute name. Let's use it. Yeah.
I mean, it fits what the model does, right? And
It was
every
like
step
transforming,
actually
yeah.
transforms the
Exactly,
entire
yeah.
signal it operates on, as opposed to having to go, iterate over it
Using
step by
that
step.
logic, almost all machine learnings are transformer models.
Yeah.
Oh, look at that.
That's what
All
we're doing.
machine learning models are becoming transformer
Before that,
models.
nobody thought to use
That's
the
right.
name, and so I guess we.
Yeah,
adapted.
I thought it was too simple. I was like, oh, that's exactly what I thought about it. But then, it's like I was overruled. Like everybody thought it was a great name, and they were right.
And what was
right, you
the
were
name
totally
you
right.
came up with?
Do you
Oh,
wanna
I
tell
had
them
a
about-
lot of. There were a lot of names. I mean, like
CargoNet.
There was something called CargoNet.
CargoNet.
I had like I wrote something. One layer was like convolution. One was attention. One I
Residual.
called recognition or something. That was like the feed forward net. And so convolution, attention, recognition, Google, CargoNet. But I'm
Wow, that's
really
horrible.
happy that
Yeah.
it's called
Yeah.
Transformer now, not
it's-
CargoNet.
That's horrible. Well,
think
I'm
one-
glad you were outvoted.
Yes, very,
Yeah,
very
from
happy.
wise people.
I think the reason it became such a general name is that, in the paper we were concentrating on translation, but we were definitely aware of the fact we were actually trying to create something that was very, very general, that really could transform anything into anything else. And I don't think we predicted how well that would actually work.
Yeah, when transformer was being used for images, that was kind of surprising. It's probably logical to you guys, but the fact that you could chunk up the image and tokenize each little, right?
I think that was architecturally there very early on. And so when we were building the tensor-to-tensor library, we were really focused on scaling up autoregressive training generally. It wasn't just for language. There were components in there for images, audio, text, and both on the input and output side. So Lukash said what he was working on was translation. I think he's underselling himself. All of these ideas that we're starting to see now of these modalities coming together and
They're
being
all
jointly
translations.
modeled, it was there day -10 in the transformer repository, because that's what Lukash was going after, was
Except
taking
it didn't work.
We're like 5 years ahead.
5 years
of time.
ahead.
Now
Exactly.
it works.
Now it works.
But
I mean, there was this
thing
other
is,
paper, one model to rule them all, no?
Yeah.
But it didn't use self-attention.
Yeah.
It's
Eventually it started
progress,
working.
but it was all there very early on, and those ideas were percolating, and it took some time. Lukash's goal was, we have all of these academic data sets, and they go from image to text, text to image, audio to text, text to text. We should train on everything. And that idea is really what drove this scaling effort to model the web, which OpenAI has succeeded, and now many of us are doing similar things. And so I think that North Star, it was there on day zero. And so it's been really exciting and gratifying to watch that come to fruition. We're actually seeing it happen now.
Yeah, and it's so interesting that in so much of knowledge, it is about translation, image to text, text to image, text to text.
Tensor to tensor.
Tensor to tensor. Yeah, this transformer idea, this translation idea is quite universal, and in fact, you're using it for biology.
That's right. Or maybe something that we like to call biological software, which is maybe an analogy to computer software that starts its life as a program that you then compile into something that could run on a GPU. In our case, basically the life of a piece of biological software starts as a specification of some behaviors you want, say, print a protein, this much, that specific protein, in a cell, and then you learn how to translate that using deep learning into RNA molecules that then actually, once in your cells, exhibit those behaviors. So this idea really goes all the way from not only translating, say, English into computer code, but also specifications of medicines, hopefully transformational medicines, any day now, into the actual molecules that we then...
And do you guys create a big wet lab that produces all this?
You have to.
Okay,
you have to run experimentation against nature, right? You really have to verify this. The data does not yet exist. There are tons of extremely valuable genomic data that you can download, largely available actually still openly, publicly, because of the fact that it's generally still largely publicly funded. But really, you still need data that specifically speaks clearly to the phenomena that you're trying to model at hand in given products. Say, for example, something like protein expression in mRNA vaccines or so.
Yeah, it's really quite true.
So over in Palo Alto, we have a whole bunch of robots and people in in lab coats, both deep learning researchers and folks who were previously biologists. Now we think of ourselves as pioneers of something new, working on actually creating that data and validating the models that design those molecules.
And so and you're saying that some of the early ideas of translation, a fairly universal translation, universal learner, universal translation, was there in the beginning. What are some of the major, architectural fixes, enhancements, breakthroughs that all of you have seen along the way that you think are really great additional contribution on top of the base transformer design?
I think on the inference side, there's been tons of work to speed these models up, make them more efficient. I still think it kind of disturbs me how similar to the original form we are. Like, I think the world needs something better than the transformer. I think all of us here hope it gets succeeded by something that will carry us to a new plateau of performance. I wanted to ask a question to everyone here. What do you see comes next? Like, that's the exciting step, because I think it is too similar to the thing that was there 6-7 years ago, right?
Yeah, I think people are surprised how similar it is, like you said, right? And people do like to ask me, what is coming next? As if I'll just magically know because I'm on the paper. But the way that I answer the question is to point out an important fact about how these things progress. You don't just have to be better, you have to be clearly, obviously better, right? Because if you're only slightly better, then that's not enough to move the entire AI industry to the new thing, right? So we're stuck on the original model, despite the fact that probably technically it's not the most powerful thing we have right now. But everyone's tool set, right, is.
But what are the properties that you guys want to make better?
That's
Context window,
well,
we want to make better.
One,
I'm not sure.
The generation, the token generation ability, we want to make faster.
Well, I'm not sure if you like this answer, but they're using too much computation right now.
Yep.
I think they're doing a lot of wasted computation.
We are trying to make that more efficient. Thank you.
But actually, it's about allocation, not so much about the total amount.
I'm with you.
Yes,
I'm on
yes,
your
yes.
side.
Any amount of
I agree.
computation, right? It's really about spending the right amount of effort and ultimately energy on a given problem, right? You don't want to spend too much on a problem that's easy or too little on a problem that's hard and then fail to actually provide a proper solution.
Yeah,
I mean,
very
That's a real...
The example is like 2 plus 2 right now.
Yes.
If you enter it into this model, right, it uses, you know, 1 trillion parameters.
That's right.
To
To
compute,
compute
even though
plus 2, yeah.
computers are perfectly capable of doing that in one
That's right.
operation.
So I think adaptive computation is one of the things that has to come next, right? So we know how much computation to spend on a particular problem.
Yeah.
Again,
even
that
the
was
original-
like an immediate follow-up paper that I know a subset of the authors here did was universal transformers, which targeted exactly that. So these ideas were
there.
still there.
I mean,
the original.
Sorry. Yeah, the pre-paper a year earlier with a mixture of experts, but now everybody
Yes.
Yeah.
they did it,
That's everywhere. It's kind of now folded into transformer, but it was before the transformer.
I actually don't know if folks here know, but we kind of failed at our original ambition. We started this because we wanted to model the evolution of tokens. It wasn't just linear generation, but text or code evolves. We iterate, we edit, and that allows us to potentially mimic how humans are evolving text, but also have them as a part of the process. Because if you naturally generate it as humans are generating it, they can actually give feedback, right?
Oh, you didn't tell me. Like, I didn't realize that was part of the
Oh
thing.
no,
I
no.
thought we just wanted to predict the next token.
Yeah, well, so I mean, all of us read Shannon's papers. So yeah, we were like, no, let's just do language modeling
But it's
and perplexity.
almost-
But that has not happened, right?
It hasn't happened.
That's, and I think that's also where we could. That's also, I think, that's connected to intelligently organizing your computation well,
Yes.
right? And that goes for images as well, right? I mean, diffusion models have this interesting property that they're iteratively refining and improving. We don't even have that. And yeah, I mean, this fundamental question of what knowledge should exist within the model, what knowledge should exist outside it. Retrieval models, RAG, I guess RAG is one instance of this, and also that goes for reasoning too. What reasoning should be done outside with symbolic systems, and what reasoning should be done. And it's largely an efficiency argument. I do believe that large models will ultimately learn the circuits to do 2 plus 2, but if you're adding up trillion numbers to add up 2, that's inefficient. So,
Well, in the case of Ilya's example, if asked 2 plus 2, the AI should just pick up a calculator and use the least amount of energy that we know, which is a calculator, to do 2 plus 2. However, if asked, how did you decide on 2 plus 2? You know, or is 2 plus 2 the right answer? Then it can come.
Yeah, it can go into math theory and explain from axioms.
That's right. That's
right. But then also like maintaining logic.
I'm pretty. I know you gave that as an example, but I'm pretty sure all the AIs you guys are creating is smart enough to go pick up a calculator.
ChatGPT does this right now.
Exactly. No, that's right, Jake.
I think the model's just too cheap right now. Like it's like
Still too small.
Yes, it's too
way
small.
too
It's
small.
too cheap because, like Jensen, thank you. You're like producing computation. It costs like 10 to the negative $18 per operation, or something on that order. Thank you for creating so much of it. But like, if you look at a model with like 500 billion parameters and you're doing like 1 trillion computations per token, that's still like 1 million tokens to the dollar. That's like 100 times cheaper than like going out and buying a paperback book and reading it, right? It's like so cheap. It's like, and we have applications that are like 1 million times or more valuable than like efficient computation on a giant neural network. I mean, like certainly curing cancer and that sort of thing is, but even like just like talking to anyone, talking to a person, talking to your doctor, lawyer, programmer, you know, you pay like $1 a token or more. So we've got this factor of 1 million to play with to make and if we can use that to make the thing way the heck smarter, like that would be like so amazing, because sometimes just the right word is going to like change the world.
Yeah, that's exactly.
I also think that we often don't talk about it much, but to make it smarter, the right interfaces are essential. How do we actually get the right feedback? How do we sort of decompose the task that we're doing in a way that humans can intervene at the right time, right? And if we ultimately want to build models that can mimic and learn how to solve tasks by watching us, the interface is going to be absolutely critical.
This might be a great way to do this. You've started a company, you left Google after you invented you guys worked on Transformer and you started your company. Could you guys all just quickly say something about the company and why you decided to start it? Because a lot of the things that you're describing, your company is working on, and so.
Yes. So yes, essential. We're really excited about building models that can ultimately learn to solve new tasks at the same level of efficiency as humans. They watch what we do. They're able to sort of understand our intent, goals, and start mimicking what we're doing. And that's ultimately going to change how we interact with computers and how we work. And basically, the sort of in 2021 one of the big reasons why I left was that the only way to make these models smart, you couldn't make these models smarter in a vacuum of a lab. You actually had to go out and put them in people's hands because you kind of need the world to annotate. Well, not exactly, but you want the world to interact with these models, get feedback from them, and make these models smarter. So the way to do that is go outside, build something useful.
Learning does require an experiential flywheel.
Absolutely.
That's right.
Yeah. And it was hard to do it in the vacuum of a lab, and putting something out in the world was easier at the time outside.
Yeah, that's cool. And Noam?
Yeah. Oh, yeah. So, when I co-founded Charcter in 2021, and the biggest frustration I had at the time is like, here's this incredible technology, and it's not getting out to everyone. Like, this is like the most like. It has so many uses. It's so easy to use. So like
Can you guys imagine Noam being impatient?
The value of this is like get it to like 1 billion people, let them do 1 billion things with it.
This is what Zen looks like.
He's calm.
Deep learning Zen. This is when he's calm.
Zen looks like a comparison to Noam when you're sitting next to him.
Yeah, thank God for giving us like this incredible technology, and thank Jensen and thank Google. But, like here, the ultimate, the goal is, we want to help everybody in the world.
You guys all have to go to charcter.ai. You have got to go check this out.
But,
I'm serious. You have got to go.
Yeah, let's start by doing this for real. Like, let's build something as fast as we can, get it out there, and get like billions of people able to use it. And to start with, it's like a lot of people using it just for fun or for like emotional support or companionship or like replace entertainment and stuff.
And it's really working.
It's just going to grow.
The number of people who are using it is insane. It's really, really working. Congratulations.
Thank you.
Yeah, that's awesome.
I already said a little bit about biological software, but maybe more about the why for me personally. In 21, I co-founded Inceptive. For really the need or the realization that there can be much more direct impact on improving people's lives with this technology than what we've had before was broad but not very direct. My first child was born, which during the pandemic certainly, but also otherwise gives you, at least gave me a newfound appreciation for the fragility of life. Then a few weeks after, AlphaFold 2 results came out for protein structure prediction, winning Cas14, and one of the big differences between 2 and 1 was that they started using the transformer and replaced the rest of their model or architecture with that, and so it became pretty clear this stuff is ready for prime time in molecular biology. And then a few weeks after that, the mRNA COVID vaccine efficacy results came out, and it was very clear that mRNA and RNA in general it's basically life complete. You can, RNA world hypothesis, do anything in life with RNA, but there's no data. It was for the longest time, in a certain sense, the neglected stepchild of molecular biology. And so it just seemed like almost a moral obligation. This has to happen, and somebody has to go do that.
I've always thought of it as drug design.
Yes.
But I love that you think of it as programming proteins, programming biology. It makes so much more sense, actually. Yeah, I love the concept of it, and of course this compiler would have to be learned. We're obviously not going to write this compiler.
Yes.
And so we have to go learn this compiler.
That's right.
And if you're going to go learn this compiler, obviously you need a laboratory, and you're going
to test it and to generate the data.
Yeah, Yes. This flywheel can work. I'm pretty excited, but I can see it happening. Helio?
Yeah, so I was the last one to leave. It's still very early days, but I can tell you what's going on so far. Yeah, I co-founded a company called sakana.ai.
What does sakana stand for anyways?
So it's a bit weird. It means fish. Sounds very weird in English, right, to call your company
You're
fish.
off to a great start.
Yeah. Thankfully, the Japanese seem to like that. Yeah, so the reason we named it fish is it's supposed to be evocative of like a school of fish, and we want to do nature-inspired artificial intelligence. So the analogy is to like a small fish can be quite simple, but when you bring a lot of sort of simple things together, then they become quite complicated. But people are not quite entirely sure what we mean when we say nature-inspired, so I want to dive into that a little bit. The central philosophy, right, what I try to push on researchers when they join, is learning always wins, right? Anytime that you go from humans trying to do something by hand, trying to engineer it themselves, to actually just using computers to search through the space, you always win, right? And even originally, the deep learning revolution was an example of that, right? We went from hand engineering features and just learned them, and it just worked so much better, right? So the researchers in this room, I want to remind you that the mad amount of computation that NVIDIA has given us, there are other things we can do apart from gradient descent, right? And we can use it to search through the space of what we're currently hand engineering. And actually, I would like to tell you that I think today or tomorrow, there's a sort of a time difference problem, we're actually making an announcement, right? I'm sort of surprised that we have something to announce so early, but we have some research that we're going to be open sourcing, and it's very on brand, because what's happening, what's in vogue right now is model merging. But it's being done by hand. Like we're making the algorithms by hand, how to merge these things. So what we did is we took all the models available on Hugging Face, and then used a very large amount of computation to use evolutionary computation to search through the space of how to merge and stack the layers. And let's just say it worked very, very well. So I want everyone to keep a lookout for that.
Okay. All right. That's fantastic. It makes a lot of sense, actually.
I'm also under strict orders to say we're hiring.
That's fantastic. Good job. Aiden?
Yeah, I think my reason for starting Cohere was very similar to Noam's. I saw a technology that I thought could change the world. Computers started speaking back to us. They gained a new modality. So I thought that should change everything, every single product, the way that we work, the way that we interact with all the stuff that we've built on top of computers. And it wasn't changing. There was stasis, and there was this dissonance between the technology we were faced with, for those of us in the know, and what it was out in the world doing. And so I wanted to close that gap. I think the way that I've gone about it is a bit different than Noam, in the sense that Cohere builds for enterprises, and so we create a platform for every enterprise to adopt it and integrate it into their product, as opposed to going direct to consumer. But that's the way that we want to push that technology out there, make it more accessible, make it cheaper, and help companies adopt it.
The thing I really love is this is what Aiden looks like when he's super excited. And that's what Noam looks like when he's super calm. I just love that.
Very true.
Yeah, Cohere. Okay, Lucas.
Well, I did not make.
I know, but you went on to change the world. You went on to change the world. Go ahead.
Yeah, I finally joined OpenAI after some time. Al Capone was asked, "Why do you rob banks?" He said, "That's where the money is." I think at the time I joined, that's where the best transformers were, at OpenAI. It's a lot of fun at the company. We know you can take a ton of data and a ton of compute and make something nice. And I still hope I can remove the ton of data part. We'll just need even more compute.
Yeah.
Sorry.
So do yours, and then I want to ask these guys the next question.
Yeah. So I was actually the first one to leave midway. And because kind of similar to Ashish, I was strongly believe that the way we're gonna make progress towards, pretty much software is eating the world, and machine learning is eating software, and so the most direct way is to teach machines to code, so that you're able to actually generate software and transform everyone's access. Now, this was 2017. It was a little bit too early. We did not have as good compute yet at the time. And so what we were trying to do, we tried to coordinate people instead to actually generate more data. And that's part of it. As a startup, you actually have this ability to put something in front of users and then also incentivize them. And we ended up realizing we need the new basic primitive, which is programmable money. Because programmable money is what allows to coordinate people at scale. And so we ended up building the protocol, which is a blockchain, which been running since 2020. It's the most users in the world in blockchain space. There's like multiple millions of daily users who don't even know they're using blockchain, but they are actually interfacing with programmable money, programmable value. And now we're starting to use that to actually bring back some of those tools to generate more data. And I think fundamentally, I mean, it's non-controversial in this group, but it's probably controversial. Copyright as a technology from 1700s will need to change. We have a new generative age that is in front of us. And the way we are right now rewarding creators is broken. And the only way to do that is to leverage programmable money, programmable value.
And blockchain.
And blockchain. And so one of the things we're working on is actually creating a novel way for people to kind of contribute data that then is used for models.
Yeah, that's super cool. And then you'll build a new positive feedback system into everything that we're doing, and there's a great new economy on top of it. We got programmable humans, we got programmable proteins, we got programmable money. I love this. And so one of the questions that people have is the current generation of GPT models have training data sets that are 10 trillion tokens large, which represents kind of approximately the size of the internet. Everything that you can scrape off the internet freely. So what's next? What kind of new model technologies have to be explored, like reasoning, like so on and so forth? And I'll let you guys talk about that. And where would the data come from?
From interactions. Like it needs to come from interaction with user. And that's like, you need massive platforms to actually be able to interact. You need economic value people get from this to do this. And then on the back end, you can funnel it to all of these models to actually become smarter.
And you can
do
value. That to make a model even better. But how do you get to that incredible pre-trained model, the starting point that everybody would want to interact with? Can you have models interact with each other through reinforcement learning? Are there synthetic data generation techniques? Like,
I mean, there's all of this, right? I think like kind of between all of us, we're working on every one of those techniques probably.
Yeah, I mean,
I think the next big thing that's coming is reasoning, right? I think a lot of people have realized this, and a lot of people are working on it. But again, a lot of it is being hand engineered right now, right? We're sort of writing prompts by hand and then trying to get them to sort of interact in the way that we think they should. And I, of course, think that we actually should be searching through that space and actually learning how to actually wire these things together and to get this sort of really powerful reasoning that we want.
And another way of thinking about it is models that are supposed to generate things that we want to consume as humans, media that we would like to consume, right, should be trained on all the stimuli that we would like to consume or that we can consume. So basically any type of video, audio, any type of way of observing the world, 3D information, spatial temporal information, should all just be dumped in there.
I'm also not sure if everyone understands that reasoning and learning from little data are very related. Because if you have a model that can do reasoning, then you have a little bit of data, it does all of this processing. Why is this thing following it? But it can put a lot of computation into that, and then oh yeah, that comes out. And it generalizes from way less data because of all this computation that it puts into reasoning. It's like the system 2 thing in human terms. And then from that, you can just let it go and then try to build it in as things that it will do.
Ideally, you want it to design its own experiments, so it collects the most impactful data for its reasoning to be able to continue searching.
But I do think that reasoning, when we figure it out, it will dramatically reduce the amount of data you need. But then the quality of data you need will matter much more, which is where all the interactions with the real world and people come in. So I do think that there will be a new age where we'll still pre-train on some trillion tokens, but the things that matter may be like high quality things, and it make it easier to like give people back money,
reward
value,
for
rewards
contributing that data, for pretty much teaching machine to become better and better.
Yeah.
A person has seen only like 1 billion tokens, so people learn pretty well. So there's an existence proof here.
Yes.
Yeah, that's right.
I would also argue that something that's, I mean, a lot of progress in the field has been made because of benchmarks and evals too. So like, you know, what is the grade school mathematics analog of say, automation, right? And so breaking down real-world, large-scale, real-world tasks into sort of simpler, and that gradation is also important because our models could probably accomplish some of them, and they can deploy, get more data, and then once that loop is closed, they have the right to actually take on more complex tasks. One, because they're also potentially watching, so observing what they're doing, so that gives them more data, then do more complex, give them higher order primitives, right? Like do more abstract tasks. So I do feel like measuring progress and making progress is also going to require breaking down or creating this sort of the science in many ways that we've done with some evals, but the science of automation or the science of interaction or the science of like code generation. And
Well,
then
you can't do good engineering without measurement systems.
Exactly, and that's really important. Yeah.
And so here, I got a question for you guys. What are the 3 questions you guys want to ask each other? Okay, we're just going to, somebody fire off one. First question.
SSMs. What do you think?
Awesome, too complicated, not elegant enough yet.
Oh, okay, wow.
Well, the funny thing about those is that, you know,
State space models.
we remember the pre-transformer age, right? But a lot of young researchers don't. But so when I looked at the paper for the first time, it was very obvious to me that it was a very poor man's LSTM. So all the problems that we were having back when we were trying to get these things working are surely also in these models, but it seems that because people have sort of forgotten the pre-transformer stuff, they have to rediscover all the problems. So my guess is that these things will be important, right? And we'll probably end up with a hybrid model. Right.
Well, Transformers has a recurrent step.
Exactly.
The fun fact I find that nobody's like actually playing with the fact that you can run Transformer from like variable number of steps. And like train that differently. And so like things like that is like actually exploring what we can do with recurrence, because you do like what this model does is like with every step it kind of augments more information for every token and kind of resolving things and kind of doing the reasoning. And so obviously if you only have like 6 steps, you can only do, you know, actually 5 steps of reasoning, because first actually is just getting more context. And so sometimes you don't need 6 steps, sometimes you need more. So like what are the different recurrences you can do on that? And then the other one, how do we go away from tokens? Like
Exactly. That's the bane of our existence.
I mean, with recurrence, I have this personal belief that we have never learned truly how to train recurrent models with gradient descent.
Yeah, that's right.
And maybe it's just impossible. I mean, LSTMs, I mean, SEP operator did an amazing job.
Well, that's why we did it so poorly.
It works a little bit. Then SSMs work even better, right? Because they're structured to it. But maybe fundamentally you need to train it not with gradient descent. Maybe you need to train it in a different way. Like humans are in some sense recurrent. I mean, we live in time. Our brains update in time. But it's not so clear we are trained with backpropagation. Probably not. So maybe there is a way that's just not gradient descent, and that's why it's been so hard to figure it out.
Well, guys, it's been so great to spend some time with you guys. I really hope that you get together every now and then. What amazing magic could come out next time from your interactions. We have a whole industry that is grateful for the work that you guys did.
Likewise.
It is. Thank you. I appreciate that.
Thank you.
Thank you.
Thank you. Thank you. Thank you. And I'm just going to do one. Could you guys just give me one? I'm going to do one, and I'll give everybody else. This is the first. This is the DGX1, and I wrote Ashish. I wrote this one to you, and I'll give you all of yours in your as we leave. This is for to Ashish Vaswani. You transformed the world. Okay.
Thank you. Wow.
And this is the DGX1. Here we go.
Beautiful.
Thank you very much. Thank you for doing this. Thank you, Noam. Thank you. Thank you very much. Good job. Thank you. Thank you very much. Good job. Good job. Thank you. Lucas, thank you. Ilya, thank you. All right, guys, thank you. Thanks for coming.